Okay. All right, we've started. The stage is yours. Thank you.
Hi, everyone. Okay, so today let me talk about the about the SUSY quantum mechanics. Okay. So now I'll roughly introduce what's the supersymmetry. Actually, most of you have heard about this symmetry. This is very famous, let's say, symmetry, or very well-known symmetry in particle physics. So it's some symmetry between bosons and fermions. Okay, so if you have such a symmetry, then it means that you can change in your theory bosons with fermions and fermions with bosons very roughly. Okay, that's, in other words, that means that in some sense you have some symmetry between matter and forces. Okay. So now, since I'll only consider supersymmetric quantum mechanics, I'll start with some supersymmetric algebra. Okay, so this will be the definition of the supersymmetric quantum mechanics in some sense. So roughly, you have some symmetry operator or supersymmetric charge. Okay, so what it does, if you have some bosonic state, so acting on bosonic state, you get fermionic one, or vice versa. If you act on fermion, okay, fermionic boson and fermion. Okay, so and vice versa. Okay, also if you act on fermion, you get boson. So let's say that this is very rough. Okay, so now SUSY quantum mechanics I define in the following way. So I have some supercharge. Okay, so let me call this this is an operator Q. So sometimes I'll put the head, but sometimes not. So depending. So it's operator. Okay, so I have Q and Q dagger. Okay, so it's two operators. Okay. Of course, I have Hamiltonian in my supersymmetric quantum mechanics. So, and if I have the following algebra, that Q is Q dagger gives the Hamiltonian. Okay, so it's, let me write 2 times Hamiltonian, and Q is Q equals to 0, and also Q dagger is Q dagger equals to 0. Okay, so this is my SUSY algebra, all this stuff. I'll call this quantum mechanics, supersymmetric quantum mechanics, if I have such a super charge. Okay, so this is again, so this anti-commutation relation. Okay, commutation relation. Okay, so now let me just write one realization of such supersymmetric quantum mechanics. Let's start with some Hamiltonian. Okay, so this is the standard way to introduce supersymmetric quantum mechanics in some sense. So let's say that we have some Hamiltonian. Okay, of course, the problems which you know from let's say normal the quantum mechanics without supersymmetry, there it's of course, you have seen some supersymmetric quantum mechanics examples, but maybe in standard courses, no one say that for some potentials or for some systems, you can introduce supersymmetry. Okay, so it's, for instance, if you have some electromagnetic fields, and if you write Hamiltonian, you can write this Hamiltonian also in a supersymmetric way. So, okay, now we will consider such an example. So it's not really example because it's quite general, because I will not fix the prepotential. Okay, so this example is the following one. So let's say that I have Hamiltonian. So this is sort of this like standard Hamiltonian. So I have P square here. Okay, so and then so there's a so-called prepotential. So it's, let me call this prepotential. So, and let's say that I have the following terms here. So 1/2 and here derivative of, so let me write this in this way, d with dx. Okay, so this is the derivative of this prepotential square, and plus 1/2 second derivative of this prepotential. Okay, so this prepotential depends on x, so this operator. So, and here what I have now, I have some Grassmann operators. So it's psi dagger psi minus psi dagger. Okay. So this is my system. So it's my Hamiltonian. So in case if this is, for instance, this is 0, okay, there's no such a term. And if this term it's just x squared, that means that you have just harmonic oscillator. Okay, so it's simple harmonic oscillator. If you don't have the right hand side and just dw over dx, it's just x. Okay, so now how to see that this is symmetric? It's easy. You need to introduce two supercharges. So the one q, it's just, you can write p plus I v prime. Sorry, plus e prime. So this is times psi, and another q dagger, it's just with minus sign, the prime, and here you have dagger. Okay, so this supercharge, this is our supercharge, this is our Hamiltonian, and then you can easily check that Hamiltonians can be written like q dagger. Okay, well, half here. Okay, so this is our supersymmetric model. So this is sort of example of supersymmetric quantum mechanics. So in some sense, general one, because you see, you can put any potential, prepotential which you like. Okay, here. Now, let me say one more thing. So here, of course, then you can also check what's the commutator of your supercharged this Hamiltonian. This you can do yourself. It's not so hard. So the commutator is supercharge gives 0. This is just commutator. Okay, q dagger. This also gives 0. We can also introduce Fermi number operator. Okay, so the Fermi number operator, this is the realization of the Fermi number operator. It's easy here. It's just let me see. So it's just Fermi number operator. It's just psi dagger psi. Okay, so this is Fermi number operator which we had like here. You see, if you remember in our expression. Okay, so I'll talk about this Fermi number operator. Okay. Now, again, what's the supersymmetric quantum mechanics? We have Hamiltonian, we have supercharged, we have supersymmetric algebra. This we call supersymmetric quantum mechanics. So now we can talk about some interesting properties of this supersymmetric quantum mechanics. Okay, so again, the difference from the normal quantum mechanics in some sense that here, as you see, I have now in Hamiltonian, I have some Grassmann operators. Okay. Okay. Now, of course, we can write some representations of this q dagger, everything here. Like if you write psi and psi dagger as the 2x2 matrices, then you can represent everything via 2x2 matrices. Maybe I will do that, but let me see if I have enough time. Okay. Now, so this is in general like this. Okay. So then you can consider different supersymmetric theories. So different in the following sense. So just for simplicity, what you can do, you can say that, okay, let me consider some theory just with one supersymmetric charge. So this Hermitian supersymmetric charge, okay? So let's say like we have one Q, so then you can consider also with many Qs, so it's not really, so I consider the simplest case now. So, but in order to show some properties of supersymmetric quantum mechanics, I will even forget about the Q dagger. I'll talk only about one Q, but you can do also for theories with many supersymmetric charges. Okay, so you can have many, like not only just Q and Q dagger. So let me now consider just simplest version where I only have one Q. Okay, so in case if you have just one supersymmetric charge, then of course Hamiltonian is written in terms of Q and Q. Okay, so this is your Hamiltonian. Okay, so
Ilmar Hocam, there is a question in the chat. So in case
in which, but the problem, I'm sorry, the problem that you know, I used so iPad, so I really can't see any chat and any video, anything. So please, if it's possible, just interrupt me and just ask your question. Sorry.
Okay, then I will ask the questions in the chat for you. Mm-hmm. Well, Nadir is asking why the name supercharge, I guess. So this is my interpretation of his question. Why do we call it
why we call this supersymmetry in general, or okay, the terminology supercharge comes from the term of that this is just the symmetry which we have, we call this supersymmetry. So symmetry between bosons and fermions. I'll come to that point at some, so after some computation. So I'll show that actually acting with this supercharge you can get from bosons fermions and from fermions bosons. So the symmetry which we have, the supersymmetry, it's the symmetry between bosons and fermions. Okay, so this we call supersymmetry. What's the reason? The historical reason, yeah, I don't remember. I mean, the Berezin's book, I think in at the end of 60s, he called this super analysis. Maybe because of that, people call this supersymmetry. So it's some symmetry. So it's like the symmetry which, so it's of course different than Poincare or Lorentz symmetry or any other symmetry or gauge symmetries, of course. This is something like you say between it's fermions and bosons. It's not about the space-time and other things, but still, you can. I mean, historically, people just call this supersymmetry. Now, the corresponding operator or charge, of course, then people call this supercharge. That's the reason. So, but yeah, I really so I need to. I don't remember. So if I remember correctly, the book of Berezin was super mathematics or super analysis, something like that. Probably because of that, but I'm not sure. Okay. So, but the point that we have some operator Q in our theory, okay? So, and with that operator, so we have such an algebra, okay? This is the whole business. So if you have such a, so call it as you wish. So in the books or in the terminology which we use, it's SUSY algebra, but you can use any terminology you like. But if you have this algebra, that means that your theory has such additional symmetry or some other symmetry which is related to this supercharged Q. Okay, so I hope this is that answer the question. Okay, so if there's other questions, so please just ask me because I can't see the chat, and also we can discuss these things maybe later via Slack or just write me. Okay. Now coming to the point, so I want to do everything with one Q just because it's easier, but in principle you can do with many Q or and QQ dagger. I don't want to do that for whole business. Just roughly which properties we have. So the Hamiltonian, if you can write Q as this, like as an anti-commutator of Q, then it's easy to see that Hamiltonian is positive definite. Okay, so because if you take any state, okay, so if you take any state and consider your Hamiltonian, so like let me write phi, for instance, Hamiltonian phi. So this any state, okay. So then you, of course, instead of Hamiltonian, what you can write this Q. Since this is anti-commutator, that means that it's phi 2 times Q square, and this is phi again, okay. And that means that it's just 2 times. So it's since it's square, it means that it's Q acting on phi, and this is so how to write this? So this is the square of this. So this is as a scalar product. Okay. So you see that it's the square of Q acting on phi. So that means that this is positive definite. Okay, because it's always, since it's square, it's bigger equal to 0. Okay. So this is that means that Hamiltonian is positive definite. So this is maybe the main feature of the supersymmetry. Okay, so now what's about the ground state? So the another feature that if you have so any state, so if you have some state phi and any state with energy equals to 0, this is a ground state. Okay, this means that this is our ground state. Okay. And the ground state actually it's invariant under supersymmetric transformation. What it means that if it's let me call this capital phi maybe, so just to fix that this is our ground state, for instance, this is capital phi. Okay, this is our ground state. So so just use the previous story, how you can write Hamiltonian. So just check, you can check this yourself. Okay, it's capital phi and Hamiltonian and capital phi. Just check it. Okay, this you can see that this is 0. Okay. So what it means that it's invariant, that means that if you act with Q on phi, you'll get again 0. Okay, so that means that it's invariant on the supersymmetric transformation. Okay, this you can check easily. Even just okay, using previous expressions or using just exact expression for the Q. Now the last thing, and everything with E is not equal to 0 is degenerate. Okay, everything. So all energy levels is bigger than 0 are degenerate. Okay, why it's like that? That's the property again of the supersymmetry. Let me show you. Okay, it's not enough. So let me write in this way. So let's say that we have some states. Okay, maybe I can write like this. Let's say that we have some bosonic state. So how to write that? So let me write phi is B here. Okay, so this is some bosonic state. So with some energy. Okay, so it's not zero. Okay. That means that Hamiltonian acting on this state gives this E and okay. Actually, what means that this is bosonic? You can do the following thing. So if you remember from our previous discussion here, talking about the 0 and 1. So for bosonic and fermionic, what we can do, we can act with this -1 to the f. So this is our Fermi number operator, okay? Fermi number operator. So that if you act to the bosonic state, okay, that means that this gives just bosonic state, okay? And if you act to the fermionic one, you get -1. So I'll write later because well I'll use that. So now this I call bosonic. So if you ask me what do you mean by bosonic state, okay? So that I'll check using this -1 with -1 to f. Just I'll act with this operator, the bosonic state, and if it still I get bosonic state, then it's fine. I mean the same bosonic state. If I get this minus sign, that means it's a fermionic state, okay? Now, the idea of the supersymmetry, it means that when you have some bosonic state acting with your supercharge, you get fermionic, okay? So now, that means that if I act with my supercharge on this bosonic state, what I'll get some fermionic state. So phi, let me write this is f. That means it's fermionic state. Okay. Now, well, so this E for levels with E is not equal to 0, all these levels are degenerate. Okay, what it means? Okay, what it means? It means that if I have some state with some energy E, okay, so bosonic state with some energy E, that means that I have exactly such a fermionic state with the same energy. Okay, now what I need to show that this fermionic state has the same energy, okay, level. So how to do that? Now I'll act with Hamiltonian on this state.
Can I ask a question?
Yes, please.
When we operate to the bosonic state, we get a fermionic state.
Yes.
But maybe it depends on the representation or something else that there can be also a constant next to the fermionic state. How we do know that there is not a constant?
In front
like
of
a complex number or just a phase difference maybe?
No, what do you mean phase difference? No, if it's some constant, that's not so important in the following sense. That means that you defined your supersymmetry algebra not in a sort of correct way. Then you just need to redefine your Q in a way that there's no any constants in front of that. Well, this was the question.
Yes. Yes.
So, but then you just redefine your Q again.
Okay, just a definition. Thank you.
Redefinition of Q. So then even if you keep some constant here, so even so for my proof that doesn't. So even if you have something here, let me put here some C. Okay. So let's say that even you want. Okay. Then you say that okay, I act on bosonic state and then I get some coefficient. That if you will see that doesn't matter because I'll keep this C everywhere and it will. So again, for all this business, you will get the same energy level. Okay, so then you can call this your fermionic state. Okay, all together with some coefficient. Okay.
So it's also about the uniqueness of the operator. Or that's why I wanted to ask that.
No,
never mind.
it's
It's
about
just a definition, as you
You
said.
need to do a normalization. Sorry.
It's about the definition, so it has to be unique.
Yes.
Because
So,
of the
and
way
then
I define it.
also your states need to be normalizable, and then you will get sort of 1 c squared equals to 1.
Okay, thank you.
Okay. So, for instance, you need to do this one. So FP is FP, it should be 1. So of course we assume that they are normalizable. Okay. Now acting on this fermionic state, what you get. So what I'll do, I'll just rewrite this fermionic state like this. Then I have Q and FB here. Okay. Now Hamiltonian actually commutes with Q always. So then that means that I can change Q with H, and then this gives. So this I know that this is just E time FP, and then what I get that Q E FP, and then this is just number, some number. So that means that it's E times Q, and that means that it's E phi F. Okay, so you see that you get the same energy level. Okay. That's the whole business. So the only thing what's interesting also about, so now what you need to do, maybe you can ask if you really obtained fermionic state, but not some other state. Okay, so that of course you need to check with this -1 to the F acting on this fermionic state should give minus phi F. Okay, this you need to check. Okay, so this also you can do just using this, because again. Just rewrite this -1 to the F. Okay, about this I need to talk maybe Q and then FB, and then also this Q and Fermi number operator there, so they anti-commute. So this gives -1 to F, and here no, sorry, and Q here and FP. This you can check. So this gives -1, okay? And then you can easily show that, okay, this is actually fermionic state. Now, this 3 property, it's important properties of the supersymmetric quantum mechanics, okay? And now we will use actually, why I want to introduce Witten index, because you see, in supersymmetric quantum mechanics, you can easily see that you have some energy levels. Okay, they're all degenerates. So if you have some bosonic state, then you have fermionic at any energy level, but only on the level of the ground state. You don't have such a degeneration. Okay, you see, for ground state, you cannot do that, because again, ground state, you see also it's invariant under supersymmetric transformation. So now, what we want to check if in our supersymmetric theory we have the spectrum with E equals to 0, some ground state, okay, energy, okay. Now, what does Witten index, okay? The Witten index, actually, so let me introduce, so this is the Witten index. This counts the difference, okay, so the number of bosonic states the difference between number of the bosonic states and fermionic ones. Okay, so this is we call trace of, so it's our fermion number operator. Okay, fermion number operator F. So this is the Witten index, and what it does the following. So it counts how many bosonic ground states we have. So let's call this NB. So this is ground, right? Okay, and the minus and or vice versa, it doesn't matter. So NF, and here also ground state. Okay. So this is the Witten index, which checks if there is there's some how to say, some states, some states with the energy level equals to 0 in some sense. Okay. So now let's say that our theory is supersymmetric, and we want to compute this index. What we'll get from if you will compute, and you'll get some number. Okay. So now you see, if somehow some of our states, so let's say that we have some theory, so my Hamiltonian, which I started, so, and then we want to compute this Witten index for that theory. Okay, so now so how to compute the number of the bosonic states and number of fermionic states? It's the different story. So I'll come to that point. But just right now, let's say that we know how to compute this number and this number. So then we find the difference, okay, and we see that it's not 0. Okay, so if it's not 0, that means that for sure there are some states with energy equals to 0, because that means that, so even NB equals to 0, then NF is not equals to 0, or vice versa. Okay, if it's not 0. So what it means if it's not, so if it's some number different than 0, that means that we have ground state, and that means that supersymmetry is not broken. So why it's not broken? Because if you have supersymmetric theory, you should have ground state with energy equals to 0, and that's actually, that state is invariant on supersymmetric transformation. Okay, so if you start with some theory, when somehow your supersymmetry is broken, that means that then you don't have any ground state in your theory. I mean, by ground state, I mean only the states with energy equal to 0. So what we call in supersymmetric theories. Okay. Now, so if it's not equals to 0, then supersymmetry is not broken. If it's equals to 0, but still it's possible that it's broken or not, because you see, if it's equals to 0, that doesn't mean that NB and NF both equal to 0, because it's possible that NB equals to NF, and that's the reason why it's equals to 0. Okay, the trace of -1 to F. So if it equals to 0, we don't know anything. So then we need to do some additional computations in order to check if the supersymmetry spontaneous is broken or not. But so do additional computations. But in case if it's not equal to 0, then to say it's unbroken. That means that if it's not equal to 0, there is states with E equals to 0. Okay, so this is sort of easy way to check. So you can compute for your theory with an index, and if you see that it's not equal to 0, nice. That means that you still have supersymmetry on the level of the ground state. Okay. So now, actually, this is the definition, but sometimes your papers and books, you can see also the regulated Witten index. So that means that, so let me call the index I Witten, okay? So sometimes you can see such a thing. So F, and this is regulated with e to the minus beta h. This is your Hamiltonian, okay? But this is the same. Just use the energized ion states and then just compute this yourself. It's easy. You can see that instead of this, you can write just sum over, so let's say from I and here minus 1 to the F e to the beta. Now, if I write for complete basis, then it's just the energy levels, okay, I and here I. So you can write this I running from 1 to n, whatever. So if you open this everything here, so what you'll get the number of bosonic states for ground state, okay, number of fermionic states for ground state, and then all other terms. So e to the minus beta, for instance, E1, but then also since it's E1, it's not equal to 0. That means that you have also such a term, but with minus sign coming from fermionic side. So it's minus E beta E1. Then for second level, for third level, so it's all levels you see you have in pairs. So one comes with plus sign, another with minus sign, everything kills each other. So that means that roughly, so everything here, since it's true for E equals to 0, because for all others, you always have two terms. One is plus sign, one is minus sign. Plus coming from bosonic state, minus from fermionic state, and all of them kill each other. And then after this constellation, you get exactly a trace of minus 1 to the F, okay? So this is the another representation sort of the Witten index. So now the question, so this is, I'll come to this point. The Witten index has some topological properties. That means that it's invariant under some deformations of the parameters of the theory, okay? So it's, you can deform the coupling constant and other things, sort of. And then the Witten index will be the same. So I'll show this using this example, my Hamiltonian. Okay, you see, I didn't specify what's the prepotential, but I will a bit vary my prepotential, but you will see that the Witten index is the same. So now the question, how to compute this Witten index? So again, why we need this Witten index? We need this index just because if we can compute that index, we can say if supersymmetry is broken or not spontaneously, whatever it means spontaneously, but that means for you at least that means that you have E equals 0 ground state, okay? Now, but finding this the number of bosonic ground states or number of fermionic ground states, it's not sort of easier, okay? So now we need to use some a bit more complicated tools to compute this Witten index. Okay, now if you remember, so from the previous lecture, we had such an object. You see here I had trace minus 1 to the F, A. Now, instead of A, I have here, in case of the Witten index, E to the minus beta h. Okay. So by the way, I forgot to tell you what's the beta. Beta is some parameter. It's some parameter. So actually, Witten index doesn't depend on this parameter. You can easily see. So it doesn't depend on this parameter. So how to show that it doesn't depend? So you can do this like I did here. Okay, just compute and you see that there's no any beta, but the very rough computation can be done just by taking derivative. You can easily show that dE Witten over d beta just equals to 0. So that means that it doesn't depend. So just take the derivative. So what will happen? So this derivative actually gives the following stuff. So then you have trace and inside -1 to the f, and here you have Hamiltonian, okay? And again, e to the beta h. Okay, this minus sign. So then use just commutation relation for these guys, and you can show that this is the same. Sorry, this gives 0. Okay. This is about Witten index. Now, the question how to compute this Witten index. For that, so somehow I have how much time I have. So I need to use path integrals, okay? So,
ask a question here.
Yes, please.
If the trace of the operator is different than 0, we say that supersymmetry is unbroken. But that means that there is a difference between the number of bosonic state and fermionic state.
Exactly. Yes, exactly.
And that confuses me because.
But on the ground state level, look, not on the level of when E is not equal to 0. When E equals to 0, then it's possible, of course. You see, on the level of ground state. So this is important. This is on the level of ground state. Of course, they cannot be different if E is not equal to 0. But on the level of E equals to 0, what says the supersymmetric algebra? That 3 things. So one, Hamiltonian is positive definite. Then second, you should have E equals to 0 as a ground state, okay?
Okay.
And the third one, all levels other than ground states are degenerate, okay? So now, the difference, if it's not equal to 0, then it means that you have more bosonic state or more fermionic state, doesn't matter, okay? That means that you have some states on the ground state level.
I don't understand the last part, I think. The ground state is rather bosonic or fermionic, is supposed to have 0 energy, right?
0 energy, exactly.
So then it means that there is a twofold degeneracy. So it should be 0.
No, what do you mean degeneracy?
Sorry, it's unique. We cannot say that it's bosonic or fermionic. It's unique.
Yeah, but that's true. That's reasonable question. We can say that, okay, why I'm talking about if it's bosonic or fermionic on the ground state level. This is your question. That's what you want to say?
Well, that's what I wanted to ask the second time, but the actual question is, I do not understand why is it unbroken when we got a different number of bosons and number of fermions.
No, again, we don't have number of bosons on the ground state. That's important. So again, okay, look, let me just one more. So Suss algebra or Suss quantum mechanics. What do we want from that? First, second, it's not important, but second one, which I mentioned, that there is a ground state, okay, for sure, with E equals to 0. So there should be such a state, okay, with E equal to 0.
Okay.
Okay.
Just like any quantum mechanical or field theory.
Sorry?
Just like any quantum theory.
No. What do you mean quantum? In quantum theory, ground state, it's for instance,
sorry. I forgot that.
1/2. Sorry?
So yeah, I forgot that.
Yeah, but here it's not like that. It's not possible that you have, for instance, harmonic said it's not quantum mechanical, supersymmetric theory, because it has no ground state with E equals to 0. You see? So, but here you should have ground state is E equals to 0. Okay, this you can show easily just using supersymmetry algebra. There is a state with grounds, which we call ground state, is E equals to 0. Okay.
Okay.
Now
that's clear.
Okay, good. Now let's say that I give you some Hamiltonian. What you want to do, you want to check if this Hamiltonian has eigenstates with E equals to 0. Yes.
Yes.
So for that, what you need to do, you need to solve this Schrödinger equation, blah, blah, blah. But this is, let's say that it's for us now impossible because you see, I wrote some prepotential. It's not x squared. It's not really solvable model, okay? So you can write any. So if it's not really exactly solvable, then it's problematic. Then you need to use perturbation to other things. So instead of solving the equation, what I'm saying that let's do the following. Let's count the number of bosonic states, ground states, and number of fermionic ground states. Okay, and let's see what the difference. Let's find the difference. Okay, and if it's not equal to 0, that means there are some states with energy level E equals to 0. Okay.
Okay.
That means that there is a supersymmetry. But if it's not like that, if it's 0, that means that two possibilities. So if NB ground and N minus NF ground, if it gives 0, that means that two possibilities. First, NB equals to NF ground. Okay. Then you need to check, maybe it's like that, but it's not equal to 0. So then it's still supersymmetry is unbroken. But second, NB ground equals to NF, and that's equals to 0, then it's broken. So it's, in some sense, it's not nice to check if it's
And we do not have any ground state at all at the second case.
Yes, that means that supersymmetry is broken. Spontaneous broken.
Okay, it's perfectly clear now.
Okay. So
because
for that, but this I will not do actually. So sorry, but let me mention that I will not do these two checks. So just for us right now with an index, for if you get something different than 0, then nice, you can easily say that okay, then supersymmetry is unbroken. Okay, we will use just for that reason.
By the way, when we write a number of bosonic ground state and the number of fermionic ground state is 0, it means that, I mean, we still got a state which has the lowest energy, but its energy is different than 0, right?
Yes, different than 0.
Because we are supposed to have some ground state.
It's possible that it's different.
I am referring to second case. In that case, we are still supposed to have a state.
There is no any state. No, this means that means that there is no any state with E equals to 0.
Then the ground state is different. It just doesn't have zero energy.
That's exactly. Then there's no ground state. So then it's higher than 0 something. Yes, exactly.
Okay, it's perfectly clear now. Thank you.
Mm-hmm. So sorry if I. So okay, now but of course, let me say again, I'm not going to compute this number of bosonic ground states and number of fermionic, because again, I just defined, I told you that this is like that. So you can easily check, actually it works like this. This shows the difference between them. But since it's trace -1 to the f times e to the minus beta h, okay, so that means that I will compute actual this integral. So this is what I want to do. You see, it's just I will plug this e to the minus beta h here, and I will compute this integral. That's what I'm going to do. Okay. Of course, here it's not enough to do this, because you see, here this trace only for the Grassmann, so for the fermionic part, but also one needs to do for bosonic part. But still, I'm planning just to compute this trace. Okay. So yeah, and at least show you how to compute this trace using the path integral. Okay. So this is the idea. Now, okay. So so I have 30 minutes. Okay, so maybe 40 even. So now I'll show you how to compute path integral for this. So I'll show you how to compute the path integral for my Grassmann numbers, okay, for my fermions, maybe a bit more. I can't really do this in detail, everything, but so just let me, okay, let me try to do for fermions. For bosons, I'll write just the answer, okay. I hope that will be, so it's again, very, very rough computation because I can't really introduce everything in just one lecture, okay? So let me do maybe all this computation just in case of the fermions, okay? So coming back, so what I want to compute, actually, I want to compute the following things. So instead of the operator A, I want to plug some operator e to the minus beta h. Okay, so this is the idea what I want to do. So now and then I need to compute this trace. So in order to compute this trace, you see, I just showed that this is a trace, but now what I need to do to compute, I need to compute this part. So I have some integral, and here I have, in case of this beta h, I have here phi bar e to the minus beta h and phi. So I need to compute this piece, and then I can say that what's this trace at the end of the day. Okay, so this is the whole idea. So what I need to do now. So somehow I need, it's what I really want to show, that you can compute this this trace just using the path integral. So again, I can't introduce the whole business about the path integral, but let me just very roughly show for the fermions how to do that. And then for bosons, I'll write just the answer. So now, let me do the following. So let's compute. So let's say that we have some two states. So one. So later I will do. I will take the trace, but right now just let me fix some general states. So this, let's say that I have phi. Phi, I want to write final, but final F stands for fermion. So let me write F. Okay, let me write a final, but this F doesn't. So it's just for final. So this and this F state, it's the fermionic one. Okay, so let's say that I have F final bar. So and here, what I want to compute, I want to compute some h bit minus beta h. Okay, F. So sorry, F initial. Okay, so I want to compute this one. Okay, so since since you know the transition amplitude, let me just show you how to do this on the level of the transition amplitude, and then I'll come to this point. Okay, so what's the transition amplitude? That means that you start with this final. So you have some initial state, so then you have transition amplitude. Okay, so this is Hamiltonian. Okay. And you have, so this, and then you have some t. Okay, this is time, and then you have f initial. So this you know how to compute. Okay, so in path integrals, what we really do, we divide this time by n. Okay, so instead of time, so we write like time equals to n times epsilon. Okay, so we divide it. Okay, and then rewrite this transition amplitude in the following way. So we write that this is f, and here instead of t, we write e to the minus e h and epsilon. Okay, and then fi, and this part actually we can write in this way, that it's e to the minus e h epsilon times e to the minus e h epsilon. So I just divided time by n. So later, actually, I'll show you that. Just I'll send this n to infinity and epsilon to 0. So just I divide and then rewrite this transition amplitude in this way, that I have minus e I h epsilon, and this is n times. Okay. So if I rewrite this transition amplitude in this way, and then between this e to the I h epsilon, I can plug identity operators. Okay, you can plug here identity operators. Okay, this I can do. This is since it's just identity, then just this operator times this identity gives the same operator. And then instead of identity operator, so I need to find this formula. Sorry. So I don't see where that's. So instead of identity operator, you see I can use this formula. So this one. Okay. So I'll use this formula. Let me write here. So now you see I plug everywhere identity. Now what I'll do, instead of identity, I will plug this integral everywhere. Okay. So if you will plug all this, so here what I'll do, just since I have many identities, for different identities, I will just have different indices. So let me put here I. So there's no summation I. Just this is I, and here I. So for the first one, I will put just F1. For the second one, F2, phi2, phi3, phi4, and so on. Okay. So then what will happen, that this transition amplitude I can rewrite as a integral. Okay. Integral. So integral over this d phi 1, d phi 2, d phi 3, 4, 5, and so on. So let me write. So d phi I. So this is the product now. I runs from 1. So d phi I. So you see, I have such an integral. Okay. Now, so I have n times of this. Sorry, what's this? What's this now? Okay, sorry. So now, how many? So I plug this once. So I have, since I have n exponentials, that means that I have n minus 1 identity operator. So it's I runs from 1 to n minus 1. Okay. So because I plug between two exponential everywhere. So here I also have exponential. You see, I plug between two exponentials. So Okay, now it runs from 1 to n minus 1. So I have this exponential here, e to the minus fi, okay. And then, of course, product, product of, so now these two guys, these guys act, you see, to the state. So what happens here that I have, so now fi bar, now e to the minus I h bar epsilon, and here fi, okay? So this is, and now, but I runs, of course, from 1 to n, but what means, maybe not 1, okay, from 1 to the here, should that I minus 1 then, okay, that's correct. So then what means phi 0, that phi 0, it's just f, yeah, I used the I and everywhere I, but this I, let me put here. So this is for the word initial, okay? So f0 is I initial, and f final equals to f capital N, phi capital N. Okay, so maybe I can put bar also on that. So this is the my transition amplitude. So this is such an integral. Okay. Now you see, I actually obtained the same expression, but now what I need to do, I need to compute, somehow find a way to compute this piece. Okay. So now in order to compute this piece, what I can do, I can Taylor expand for small epsilon, this e to the minus I h epsilon, okay? So since I really have just how much time, 20 minutes, let me just write the correct answer. So what one needs to do, again, let me just copy this and just write that you need to Taylor expand, okay? Okay, so just Taylor expand this piece, expansion, okay? And if you will do this Taylor expansion, all this business just gives, so it's just e to the minus e h, so it's just e h f, so now h, of course, depends on f, f bar I and fi, okay, minus 1. Okay, and then some boundary term e to the f fi bar and fi bar f I minus 1. So this is what we will get. So just Taylor expand, okay, and then act with your Hamiltonian for any phi I. So what this means, that you act with your Hamiltonian to the so let's say that you have Hamiltonian, and then you act to fi. Okay, so that's what you get. So now it's not really Hamiltonian, but this is the iron. So it's it's not the Hamiltonian, but it's the iron function. Okay, so it's some function now. Now, if you will do this, just go back and plug this this expression back to this integral, okay? And if you will plug this back to the integral, you can easily see that this expression actually gives the action, okay? So how to see that? Now maybe I can do this smaller size. So okay, put this clean. Now if you plug it back, so this is the standard technique in path integrals. Okay, so so you have the same product, everything, but now so I'll not write the measure. So the measure is the same. It's always like this. So I'll just write the exponentials, okay? All exponentials together. So now what I have e to the minus phi I. So everything now it's just numbers. So there's no any operator anymore. Phi I, okay? And then minus, I forgot epsilon here. There's epsilon also. Epsilon h phi I minus 1, and then also phi plus phi I bar phi I minus 1. And since we had here product, this product can be written as a summation here. Okay. Now, if you write as a summation everything here, then what you need to do, you need to, so for instance, just take these two terms, okay, and then rewrite these two terms in this way: e to the phi I bar how to write phi I bar is minus 10. So this is phi I minus phi I minus 1. You see? So this looks like a derivative. Okay. So in order to write this as a derivative, what you can do, you can divide this by epsilon and then multiply by epsilon. Okay. So we will send epsilon to 0. So then another term, you just write minus h. So we have I in front of that. So we have I, h. So let me forget about the I, because I can, so this minus 1, let me write as a I squared. Then I have I here and here I again, and then Hamiltonian, just Hamiltonian. So Hamiltonian fi minus 1. And then everything times epsilon, okay, everything times epsilon, plus you have this bounded term. So coming for the bounded term, you need to add, because the last term, of course, it's the bounded term. So it comes from here. You see, since this summation goes from 1 to n, you have here phi n. Okay, so I just plus bounded. I don't want to write bounded terms. Now, so this piece, this exponential piece, of course, you can write as a integral now. Yes, so it's e to the I, and then it's just integral from 0 to t. Okay, and here you have dt, and then this stands for the derivative now. So you have phi bar, now phi dot. So this is derivative of phi, and then minus Hamiltonian. Okay, so this is the way how to write. So now you can easily see. So actually, okay, you can't see this, but let me tell you that for fermionic part, this is just the action. So, but of course, I forgot to tell you what's the action. I just wrote the Hamiltonian, but when you have Grassmann numbers, the action actually can be written in this way, but okay, doesn't matter. So whatever. So in our case, we have Hamiltonian. So this we call path integral. Okay. So now, and when you send the n, so since you send epsilon to 0, that means that you send the n to infinity, and instead of these two guys here, what we have d phi. So this is notation, because now I runs from, not from 1 to n minus 1, but runs from 1 to infinity. Okay, bar, and here we have d phi. Okay, so this is the whole business, how to do that. And you see that we can, instead of using this number of bosonic and fermion ground states, we just can do this computation via path integral. Okay, so now what's important here that since we use so since we will do this for the case where we have not only this one, but also -1 to the f in front in the trace. So then that means that we use the periodic boundary conditions. If you remember, we had here periodic and anti-periodic boundary conditions. So here, if you remember, we had just phi bar phi, but when you just compute the trace, you have -phi bar. So if you just compute the trace as a partition function, then you need to use anti-periodic boundary condition. But when you compute the width index, you need to use periodic boundary conditions. Now, at the end of the day, what's the expression? So the expression is the following. So the trace -1 to the f. So this, if you plug this, that means that you have periodic boundary conditions. So okay, with minus so now this is our Hamiltonian times t I h t. That means that you have such an integral with, so here is periodic boundary conditions. Okay, and now you have d phi bar, d phi, and just you need to compute this I s, which depends on phi bar and phi. Okay, so this is for fermionic part. So now, what we need to do, we need to compute such a path integral. Now, in case of bosonic, probably you know how to compute these integrals. I don't know if you are familiar or not, but for instance, for the harmonic oscillator, it's just a sort of Gaussian integral. So okay, let me just show you one example now for bosonic part. So example. So now, in case of bosonic part, you have again this periodic boundary condition. Okay, boundary condition. And there, what you need to do, you have this again product over this all passes. So that's just dx, and this is t. And then you have so exponential. So now I'm not computing this sort of. So just let me show you just how to compute, for instance, partition function. So instead of, so in case of the partition function, what you need to do, so instead of this sort of I and t, you just plug beta. So that means that you don't have here I anymore. Okay, now, so if you compute the partition function, so partition function, it means that just z equals to e to the, so it's just trace, let me write it like this, z equals to the trace e to the minus beta h. Okay, so if you compute the partition function, for instance, for the harmonic oscillator, okay, so in case of harmonic oscillator, we know that it's just 1/2 p squared plus 1/2 x squared. Okay, now if you do this for the harmonic oscillator, what you really get, you get e to the here integral from now, not from 0 to t, but from 0 to beta. Okay, and then dt, and here what you have just for quantum mechanical problem, you just use the classical action. So here what you have x dot square over 2 plus x square over 2. Okay, so you need to compute this. Now, since it can be written as a Gaussian integral, yes, so it's just by doing integration by parts, this piece you can write as a 1/2 x d square dt square x. Okay, so just, and you see this is Gaussian. This is this part, some operator acting on x. Okay, so since it's Gaussian integral, we know that the answer, I'm not sure that everyone knows, but you can easily compute yourself. So that gives, so if you have some integral with, let me write somewhere. So if you have some integral here with x and ax, I asked you to do this for Grassmann variables. So if you have such a thing, so then what you get 1 over so 1 over square root of determinant of a. Okay, so not so 1 over, but still it's some p and some coefficient, but it doesn't matter. Now, in this case, what's our operator? Our operator is the following thing. So our operator is the you see, if I put here some parameter, so let's say omega square, like in harmonic oscillator, what we have just 1 over square root and determinant of minus d square dt square plus omega square. So from this operator, you need to for this operator, you need to compute the determinant. So, but when you compute, of course, the determinant, what's important, you also need to keep in mind that you have periodic boundary condition. That means that x, so periodic boundary condition means that x at 0 equals to x at beta, okay? So if you compute this determinant, then you know the answer for the partition function. So what's the, in case of the harmonic oscillator, it's really easy. Just you need so you need to find what's the eigenvalues. So what to find? So maybe next lecture I'll show you. Find eigenvalues of this operator. Then the product of the eigenvalues gives the determinant. Okay. Now, so you see, this is the way how to compute the such path integrals. Okay, you just need to rewrite your integral in the way in the Gaussian way. Okay, and then you know that it's just determinants. Okay, now coming to the Witten index very roughly now. So if unfortunately next I'll compute for my system and show that it's topological invariant next in the next lecture. Okay, but still the answer is easy to write, because now what we need to do, we have some Hamiltonian, so maybe I can copy that. So this is our Hamiltonian. Okay, you start with this Hamiltonian. Okay, copy. Plug in your path integral. For Grassmann, you use this integral. Okay, for bosonic part, you use this integral. Okay, so if you do this, so maybe okay, like this. Okay. So now what really we need to do? We need to write this Hamiltonian in our path integral. Okay, so again, since we compute sort of partition function, or this is special partition function, what we call Witten index. Of course, there you also in the case of path integrals, what you really need to do, you just write your everything so in terms of the Euclidean action. So then just trace -1 to the f e to the beta h. It's just with periodic boundary conditions, you need to compute such a path integral. So it's e to the so let me write minus action, okay? But since you have Hamiltonian, you can always write action in terms of Hamiltonian. So and here, of course, this integral over Grassmann and bosonic variables. Okay, so you compute this partition function, this path integral. So the answer, what's the answer? So very roughly, I'll show later. It's just you will get some determinant for some bosonic operator, okay, and for some fermionic operator. So this is for fermionic one, determinant from, and then you will get also determinant of some, so 1/2 square root of u. Right. The result will be just determinant of some operators. So then you need to know how to compute this determinant. Then you are done. You know what's the witness for the system. So maybe I should stop here because this is the hardest piece of my talk, and I was very fast here. In my next lecture, I'll show you how to compute this. Actually, it's not really very hard, but still. So, and if you have questions, please ask.
Thank you so much. Let's have a few questions if the audience have any. Okay, there doesn't seem to be any questions. So I'll stop the recording first.
Mm-hmm.